This video covers waves. Now this will be a review from last year. When two waves are in phase, that means that their crests and wavelengths are the same. Now their amplitudes don't need to be the same. When they are out of phase, that means that their crests do not line up. When they're 100 degrees out of phase, that means that their crests and troughs line up instead. Now we can have two different things happen when they are in phase or out of phase. When they are in phase, we have constructive interference. That means that if I have one wave that's coming in, and if I have another wave that's coming in, again, both of these waves are traveling towards each other, in the middle, their amplitudes are going to add up. And then afterwards, they are going to continue on as if they never met. So this wave on the right-hand side was this wave initially. This wave on the left-hand side is this wave. Again, here in the middle, they do meet. On the inside, this is essentially what's happening. And then afterwards, they just pass each other. When you have destructive interference, the opposite happens. So let's say that you have one wave that's coming in with a crest, and you have another wave that's coming in with a trough. If their amplitudes are exactly the same, they're actually going to cancel each other out right in the middle. But then again, afterwards, they're going to continue on as if they'd never met. So again, here on the left-hand side, I have the blue one that was always at the bottom, and on the right-hand side, I have the right one. Now, this only happens if the amplitudes are exactly the same. If they're not, then you're only going to produce a smaller wave. And I'll show an example over here. So let's say I have a greater amplitude and have a smaller amplitude. When they meet in the middle, I'm still going to have some amplitude, but again, it's going to be smaller than it was before. Afterwards, they're going to continue on as if they never passed each other. So again, this one is going to the left and this one is going to the right. Again, stuff from last year. We have incident waves. This is the inbound wave. I'm going to draw this in red. We said that if we have a wave, it's going to go into this boundary and then hit. When it hits this boundary, if it is a fixed boundary, that means it's not allowed to move, it's going to come back to us, it's going to get reflected, but it's also going to get inverted. So I'm going to draw that in blue. This is the reflected wave. Again, these are supposed to be perfectly symmetric. Now, in blue is my reflected wave, in red is my incident wave. But if this happens so often, it's going to look as a standing wave. And we're going to have points of nodes where we have 0 amplitude. And we're going to have points of antinodes where we have maximum amplitude. Again, that happens here and here. And again, nodes happen where there is no amplitude. So this is what that picture should have looked like. Now, remember that from last year, a complete wave would be from this point all the way up until this point. So that would be one complete wavelength. So again, from this point to this point would be one complete wavelength. Here we see only half a wavelength. On the AP exam, the bottom pictures are what you're going to see most often. Now, just a reminder, a couple of things about sound waves. That pitch is determined by frequency. So the higher the frequency, the higher the musical sound, the musical pitch. Loudness is determined by amplitude. So the greater the amplitude, the louder the sound is going to be. Remember that the human range for hearing is 20 to 20,000 hertz. Anything above that is known as ultrasound or ultrasonic, and anything below that is known as infrasonic or infrasound. So oscillators have natural frequency. This is known as F naught. This is your resonant frequency, also known as your fundamental. If you apply a force repeatedly to an oscillator at the resonant frequency, then the amplitude of the waveform is going to increase with each application of force. You can think of pushing on a swing. If you were to push just at any frequency, then your swing might not go as high. But if you push at the right frequency, then it's easier to get the swing to swing all the way up without as much effort. Now, a couple of equations. We have two. This first one is velocity is equal to frequency times wavelength. Again, frequency is units of hertz. Wavelength is distance, so it's in units of meters. And velocity, always meters per second. Now, this in particular is the velocity of a wave in medium, and we're going to see different examples of this in a bit. This bottom equation is new. Here, we're solving for the velocity based on the tension in strings. So Ft is tension. I didn't want to use T because we're going to most likely see period as well. Here we have mass and length. This is also known as the mass density because it is a mass per unit of length. So you're saying that your mass is being evenly distributed over the entire string. So let's say that the velocity did not change. If velocity was constant, let's say in sound, then if my frequency went up, my wavelength would go down. And that makes sense because if I have a smaller wavelength, then I can, and in a certain amount of time, my frequency would go up. If my wavelength were longer, then the frequency would obviously go down. Again, frequency is how many cycles happen per unit of time. So again, less cycles will happen in more time if my wavelength were very large. Now, this is where the most of the AP exam is going to focus on as far as waves go. Here we have an equation for the length of our string, which is L, length of string. N is the number of antinodes. This is also going to be known as the harmonic number. So this is one antinode in the first picture. This is two antinodes in the second picture, and we have three antinodes in the third picture. So this is known as a first, second, and third harmonic. So we can use this information to help us figure out the wavelength and eventually the speed in different pieces. So let's look at the first one. Here, if I have one antinode produced, that is not a whole wavelength. That is only half a wavelength. So again, I'm putting a 1 in as my N, and I have 1/2 of a total wavelength fit in that length L. In the second one, I actually have a total wavelength produced. So my antinode is 2. So 2 over 2 gave me 1, so I have 1 lambda. Here I have more than 1, so I have 3 over 2 fit in that current length. And then we can rearrange these equations to actually solve for the wavelength, depending on the information that we have. So again, we can use these wavelengths to help us solve for the speed of a wave in strings. Again, this frequency that we are using has to be the frequency of the fundamental if we're only dealing with one antinode. Here, we're dealing with the second harmonic, or 2 antinodes. Here, we're dealing with the third harmonic, or 3 antinodes. Now, this is for open tubes, meaning that you have opening at both ends, or an antinode at both ends. Again, our equation is going to be the same as that for strings. Again, n is the number of antinodes. This is also known as your harmonic number. And if we plug in our antinodes for our n, then we can solve for the wavelength at different points. Again, we can use that information to help us solve for our velocity. And again, this is known as your fundamental. The second one is your second harmonic. And the third one is your third harmonic. Here you have our equations for a closed tube, meaning open at one end, closed at the other. You'll find a node and an antinode, or half an antinode, where n is still the number of antinodes. Remember to include our new equation. This new equation has a 4 instead of a 2. And the reason for that is how the wave travels inside of this particular tube. Now for n, you're going to need to count these twice. So here you have half of an antinode, but we're going to call this times 2 would give you 1. This is 1.5 times 2 gives you 3. Here we have 2.5 times 2 gives us 5. So this is a first, third, and fifth harmonic. Here, only odd number harmonics would be produced. Again, you can use all of this information to help you solve for wavelength, and then use that information to help you solve for your speeds. Again, for the first one, this is my first or fundamental. This is my third harmonic, and this is my fifth harmonic. Again, only odd number harmonics will be produced in closed-ended tubes. Now we move on to the Doppler effect. Doppler effect comes from the movement of the source or the observer. So when nobody is moving, you have sound waves that are emitted from a stationary source, meaning they're just radiating outwards. So this is what you would hear if nobody was moving. Let's say that you were an observer on this side of the source. The wavelength, if our source is moving towards you, our wavelength is going to become smaller. So if our wavelength gets shorter, our frequency gets higher. If our frequency gets higher, that means you hear a higher sounding pitch. Now the opposite happens if you're on this side. By the time these waves get to you, the wavelength is now appearing to be longer. So a longer wavelength is going to give you a lower sounding frequency. So that means you're going to hear a lower sounding pitch if you're behind the source. So, when a wave source moves towards an observer, the emitted wave appears to have a higher frequency, and the wavelengths appear to be shorter. Sound waves will appear to have a higher pitch, and light waves will actually do this too. They're going to appear to have a blue shift, meaning a blue tinting, and we'll see that when we talk about the electromagnetic spectrum. When a wave source moves away from an observer, it appears to have a lower frequency, meaning that the waves appear to be longer. Sound waves will have a lower pitch, and light waves are going to be red shifted, meaning it's going to have a red tint. Finally, we have a situation where the sound source is moving slightly faster than the speed of sound. When that happens, the sound waves are going to pile up in front of the sound source. This is known as the sound barrier. For this to occur, the sound source must move at the speed of sound, which is 343 on average. This is also known as Mach 1. Now you can actually move faster than the speed of sound. When that happens, the sound source outruns the sound waves. This leaves a wake of sound, like a boat wake, behind the source. This wake of sound is known as a sonic boom, and the sound source is said to be supersonic. And then finally, our equation for Doppler problems. Remember that if our object is moving away from the source, then we're going to have that negative symbol. Don't forget there's already a negative there, so that's not something that you change. You're just going to substitute in a negative value for Vs if my source happens to be moving away from my observer. But we'll see problems like that in class.